So, good afternoon and welcome to this last lecture of Communication Network 3 for 2020. So, yesterday we finalized the first block of conceptual block of lectures. So now we finished with the preliminaries and the main concepts of quantum mechanics. And in this lecture and in the other two, we will explore the contextualization of those concepts into computing and communication. Especially the concepts that I will present in the course of this lecture will be important in the lecture we will have, the first lecture in January after Christmas break, because as you see, I put like lecture and exercises because I plan to set up interactive lecture in which we will see, we will combine the blocks, the circuits, the blocks of circuits that we will see today in order to experiment, if I can say this, the combination of these blocks and the operations on circuits on a software. So we will do like an interactive online lecture. So, and finally, I will show you some concepts of quantum communication networks and the quantum internet. So I would say that now you can breathe, and because I would say that the hardest part of conceptually, the hardest part of the module has finished. So now the concepts that you have acquired, that you got during the previous lectures, will be just contextualized. So we will see just specific applications of what we have already seen. So this is exactly in our conceptual summary what I have just said. So today we will see the concept of non-locality, qubit, measurement, entanglement, etc. In the concept, in the theory of quantum circuits towards quantum computing, and with some words on quantum programming. So these ones are the postulates that we have seen in the previous lectures. This slide is just to give an overview of the basics that we need now, that we borrow from quantum mechanics. So the first postulate, we saw that a quantum system is represented by a vector in the complex Hilbert space. And we saw that a qubit is the superposition of the basis of this two-dimensional system. And so we saw the difference between a classical bit and a quantum bit. Then the second postulate, we analyzed the various characteristics of the Schrödinger's equation. We showed that the evolution of a quantum mechanical system is deterministic and not probabilistic. So given the Schrödinger's equation and the specific Hamiltonian of the system, then solving the Schrödinger's equation, we can have the unitary evolution of the system. So this is deterministic. On the other hand, what is probabilistic, because of the, let's say, still incompleteness of quantum mechanics, I believe, and not only my opinion, but still the non-existent interconnection between the macro-physical theory of relativity and space-time is not conceptually connected to the quantum mechanical theory, then there is this collapse of the wave function due to measurements. Measurements is performed applying these linear quantum operators that we saw for the momentum, the positions, etc., that are the physical observables that are represented algebraically via Hermitian operators. So we saw what is an Hermitian operator. We saw all these concepts and background. Then here we have the result, that is a vector that one of the possible vectors related to one of the possible eigenvalues. So one eigenstate related to its eigenvalue, and the choice of these eigenvalues and the respective eigenvector is probabilistic. Then we saw that not only like isolated single particle quantum systems exist, but we have actually in reality very likely composite quantum systems, so systems of more than one particle. And when we analyze the structure of the wave function, consider the input given by the Schrödinger equation and the analysis performed on a single particle quantum system, theoretical analysis, we see that we have a huge number of states that are linear combinations of the composition of the 2, 3, 4 multiple quantum systems. So this huge amount of states that are not decomposable, that cannot be written in the product in terms of the outer product of the single separated quantum systems, this huge number of states are called entangled states. So is the part of the Hilbert space, the composite Hilbert space, that is represented by the degrees of freedom of the entangled states. So this is more or less what we have seen. Also, we saw what these entangled states imply. So these states give a kind of correlation that somehow changed according to what Einstein, Podolsky, Rosen were thinking, and also till the scientific community had the idea of non-locality, locality till that moment. So the classical idea of locality changed because of these characteristics of entangled quantum states and the behavior of these states. However, we saw that it's not this idea of locality is slightly changed, but is not undermined. So entanglement still satisfies locality. So this implies that it's not possible to violate, for example, the principle of relativity that the speed of light is the maximum speed achievable. So this is like the recap, high-level overview of all the things that we have seen in the previous lectures. So now we see some applications, for example, of the concept of the entanglement. Before going to the presentation of the circuits of the basics of quantum computing, I wanted to show you an example of how entanglement in communication and computing and distributed computing can give a gain that is impossible to be achieved by classical approaches to solve. And this introduced the concepts. If you are familiar a bit with game theory from other courses, here I will just mention the basics. So I don't need to introduce game theory, or because I will not borrow concepts like complex concepts from game theory. Everything that you can just get from these slides. But this extended the theoretical background of game theory to games that include the possibility of quantum mechanical phenomena like entanglement that in classical games were not possible. This one example of these games is an example that you can find also in the internet, a lot in the literature, etc., is the CHSH game. So that is connected also to the example, the second example that I showed yesterday. I will recall it here for entanglement. The example now I will show you how this can improve some communication and computing characteristics. So if we look at the Bell experiments, so the results of Bell after the APR experiments, so the fact that the APR experiments were trying to find hidden variables, classical variables to explain entanglement. However, these experiments opened the research to find how this, in reality, how these statements, experiments were violated. So it produced experiments that brought to some inequalities that were giving a description of the behavior of entanglement in respect of classical systems. So this is just a high-level Routh description. So these behaviors of and achievements of entanglement, these inequalities, can be seen also from another theoretical perspective. So from the perspective of game theory. So in the case that we have like spatially distributing parties that are cooperating to each other. So if we imagine, for example, that we have 3 parties, these 3 parties communicate with a referee that is the third party verifying, sending the challenges and the receiving and checking the outputs. Then we see that the violation, as I said, of these Bell inequalities represent the winning strategies that via entanglement can be achieved. So this game, as I said, is called the CHSH from the respective inequality that the scientists Clauser, Horn, Shimony, Holt wrote, described in 1969. So just brief introduction of terminology in order to understand the mathematical context of these quantum games, just to speak the same language. So we know that game theory is analyzing like situation of conflicts. In fact, is used a lot in economy, in social analysis, etc. And it gives a mathematical study of conflict situations considering entities performing rational decisions, so with rational decision making. So as I said, classical game theory can be generalized to quantum game theory if in the strategies we include also the possibility of some quantum mechanical phenomena that are not existing in the classical domain, in classical physics. So classically a game consists, as I said, you need n players that are in a specific situation. These n players are rational, assumed to be rational. And these players and the game is defined by the rules. So a play is every particular instance that in which the game is played. So considering the rules, instances of chronological instances of the rules, and as I said, the game is a sequence of moves and strategies, and these single moves are in a chronological order. So the moves can be like personal moves, so choices that each player performs depending on the individual decisions, and there are chance moves that are the choices influenced by external things, so not just on the rationality, the individual rational decision making. So then the rules of the game can restrict communication, so the exchange of information among the players. So we have in a game, obviously, the payoff function. So this function should be maximized because it implies the success of the players to play the game. So is the award that you get is a real number, and the scope. So the scope of the game is to maximize this payoff function. In the context of these quantum games that we mentioned, we consider cooperative games. So cooperative games, this is a distinction because it happened to me sometimes when talking to other colleagues, etc., that this distinction was not clear. The games can be cooperative or non-cooperative. So cooperative games consider coalitions of players. So they perform joint moves and strategies. If you consider non-cooperative games, like for example, cooperative games were theorized a lot by John Nash. If you have watched the film A Beautiful Mind with Russell Crowe, so the non-cooperative games are another kind of games in which the players play individually. So the payoff functions are individual. And they have their own move and strategy. So not coalitions are not considered. Moreover, we say that in this case, for the games that we mentioned here, like the CHSH, we consider non-local games that are a subset of cooperative games with incomplete information. So the communication between, as I have just mentioned in the previous slide, the communication between the parties, between the players, is incomplete or absent. So parties can either communicate partially or not communicate at all. So the CHSH inequality translated into game theory is falls under the definition of cooperative game with incomplete information, so non-local cooperative game. And here we have the representation of what I have just introduced. So imagine that you have the three entities that I mentioned. You have two entities, communicating entities, Alice and Bob, and a referee. This, for example, I just put this picture. This, for example, can represent outsourcing like a computing task to two different data centers or servers. So the referee is also called verifier. And what the referee does is sending like two challenges to the respective players, so Alice and Bob. Alice and Bob independently perform a function on this challenge, and then they produce an output. They send back the output of this challenge to the referee that finally checks if the answer to the challenge was like successful. and then it is possible to see the payoff function. So imagine that, as I said, the referee sends 2 bits like X and Y, and now the game is to perform this function in the CHSH game. So you have to check that the logical end obtained, so the referee checks that the logical end obtained on the bits that he sent to separately to Alice and Bob is equal to the XOR operation of the bits that are sent back in response to his challenge bits, so the XOR of these 2 bits. So if this is correct, is satisfied, this equality, then the payoff function increases. So all the times the probability, the objective is to maximize the successful, so the satisfaction of this equality. So, for example, we can see that if we consider, for example, that we have X and Y, so we have the logical end, and we need to verify their XOR. So if we have this table, then we have, by sending, for example, 2 bits X and Y, we have the 4 possibilities that are the 4 bits. So we have the result of the logical end, and 1 when every term is 1. And so according to the bits that are sent by sent back by Alice and Bob, we see the evaluation of this expression. So, and we check if the referee checks if it's equal to the. So if we imagine, for example, that you can try the various possibilities by your own, but if we imagine, for example, that Alice and Bob send all zeros, like this, then we see that the results here will be all 0. So if we check these columns to verify, to find the payoff function, so the successful satisfaction of this equation, we see that we have a payoff function FC that is the ratio between 3 times satisfied over 4. So we have a success of 75%. So this is here is explained what I have mentioned, so that there is a classical payoff function with maximum to maximize the probability of a successful game. Then what we have seen in the example that I mentioned is like the pure deterministic strategy. Then there are other classical strategies that are probabilistic strategies, in which the two players, Alice and Bob, share a private randomness. And then there is a case that is the shared randomness, in which the referee gives to Alice and Bob before the game starts a common random sequence of bits, in the way that it creates a correlation between Alice and Bob. However, even in this case, in which there is a shared randomness, so there is a partial communication, a partial correlation between Alice and Bob, even in this case, the outcomes of probabilities that now are conditional probabilities, and not just the deterministic probabilities that we have seen for the pure deterministic case, but now we have the conditional probabilities of the results conditioned to the specific correlated randomness, but at the end we obtain anyway 75% of maximum success. So the maximum of the payoff function that can be achieved classically is 75%. So now player A and B, we consider, so now we consider the possibility of using entanglement. So we consider the possibility of using quantum strategies. If you remember if you remember the example that I showed yesterday about entanglement and measurement on an APR pair, a singlet, if you recall from yesterday the percentage of successful success that we saw yesterday, according to the measurement in specific basis, you can see that there are possibilities by using specific basis to exceed this 75% if we consider that here we have a referee that sends the challenges and then gets back the results. We can see that this time, thanks to entanglement, we can achieve a payoff function till 85%. So just by sharing an APR pair before the game starts between Alice and Bob, then we can achieve a success like 10% more, about 10% more of what was achieved by all classical solutions. So we see that in terms of what I mentioned also in the previous, in the first lecture that we had when I was talking about communication complexity, here you see that the communication was 2 bits of communication. So given these 2 bits of communication, in the classical case, you have 2 bits of communication or 2 bits plus a shared randomness, but nothing changes. So the maximum success that you can get is 75%. With a shared entanglement and the same 2 bits of communications, you can achieve 75% of success. So this quantum correlation given by entanglement can increase of a factor of about 10% the payoff function of the CHSH game. So you can see with this example one of the possible benefits that entanglement can give. So now let's move to the other block of conceptual block of this lecture. So the quantum circuits. So the idea behind the quantum computing is not merely, I mentioned in the first slide, sorry, in the first lecture, is not merely to enhance classical computing, but also there are problems in simulating the behavior of quantum systems for like numerical simulations or in physics, etc., that are not possible to be achieved by classical computers. So the complexity is so high, and we see this problem in the scientific community since we try to, there are works trying to, of scientific research groups like ours as well, to try to simulate quantum communications and quantum communication systems via classical simulators. But the complexity and the resources needed are huge, increasing the number of qubits that you allow in the communication and the number of nodes. So classical systems are quite inefficient and cannot afford simulations of quantum system and quantum communication systems. So it's not merely improving what we do classically, just applying quantum. Is that there are problems that are not solvable, and quantum computing is the only way that can lead us to solve those problems. However, if we realize quantum computing, doesn't mean that we just take the classical algorithm and we program it in the quantum computer. No, this is not true. The quantum computing framework, conceptual framework, implies that the classical algorithms should be rethought and rewritten in order to be efficiently contextualized in the quantum context, in the quantum computing context. So this is another important aspect that should be taken into account. And what made like classical computers successful was that if you have like you have a small set of instructions, basic instructions that the CPU performs, and with those small set of instructions and operations, you can solve any problem as a combination of those instructions. So this can be also seen in this so-called Church-Turing thesis, so that any function can be computed by any means, and compilation, the concept of compilation means that the decomposition of a problem, an operation, into sequences, a set of sequences of instruction, is the definition of compilation. So important in the context of quantum computing are the so-called De Vincenzo's criteria. So in 2000, this researcher, scientist De Vincenzo, published an article that afterwards became a guideline for the development of quantum computing and quantum communication. In this article, he was providing 7 points, 7 guidelines, 7 rules that should be satisfied to achieve a successful quantum computing implementation and also quantum communication. So the first is related to a scalable physical system with well characterized qubits. What does this mean? So if we have a quantum computing system, we need that the qubits and the parameters of these qubits are known. So the Hamiltonian of this quantum system, systems that are used in computing are known. So even the couplings among states and interactions with other qubits and or other or external fields that can influence this quantum system. Then the second De Vincenzo criteria is referred to the ability to initialize a qubit. So the first is that we have to have complete knowledge of the qubit. Then we have to be able to initialize the state of this qubit. So the pillar of classical computing is that you can initialize the registers and the value of the data before starting the computation on it. Then the third the third point, in that sense, in the second point, sorry, we have quantum error correction that helps. We will not have time to go into the field of quantum error correction in these few lectures in this module that we have here, but there is a field of quantum error correction related to this to maintain the quality of the qubit, avoiding the errors in the computation. So the third Di Vincenzo criteria is referred to the coherence time. So yesterday we saw what is coherence and decoherence. So if we have entangled systems, quantum systems, the coherence also in normal qubits, not entangled, we have the superposition. The superposition of the basis, so the quantum system includes all the possible superpositions, all the values given by the possible superpositions. And this is the coherence of the quantum state. So if we lose this coherence, then we lose the the power of the computing power, the computing capabilities of the quantum bit or entanglement or entangled quantum systems. So we want that the decoherence time is much longer than the gate operation time, because for all the period that the gate performs operation on the qubit, we need that the qubit is in coherent state. So the fourth criteria is that we have a universal set of quantum gates. So the thing is, in quantum computing, we have operations. We saw the definitions in the previous lectures. So what is unitary evolution, what is measurement, etc. So in quantum computing and communication, is very critical, not like in classical computing and communication, because here is very critical the difference between the unitary evolution and the measurement. And we saw it comparing the Schrödinger's equation and the measurement process. So what we have is that the quantum gates, the quantum circuits, perform a series of unitary transformations of the qubits, and the measurement is at the end. So, because the measurement destroys completely the qubit. So we saw yesterday the projective measurement that at the end projects the input qubit into one of the possible eigenstates, and then is not reversible. So also we have to control as I mentioned yesterday regarding the Zurex model, that we have to take into account the entanglement with the apparatus. This is quite important because is probably hard to say that in a quantum computer the qubits used will not be entangled with the apparatus, the computing equipment itself, but at least we need to guarantee that this entanglement is negligible and doesn't affect the computing operations. So these are important aspects that are critical. Even now are significant limitations in the realization of quantum computing entities and quantum communication entities. So this is a critical challenge that companies and scientific community are facing for implementing quantum computers and the quantum internet. So the fifth the criteria is referred to the measurement capability. So you have to be able to access the results of the computing, and this result should be a reliable access to the result, this access, because is the basis to have the fundamental to have an efficient computation. So there is, in that sense, a trade-off between the complexity and the reliability, but also between the measurement time and the coherent time, because a fast measurement permit also more time to perform error correction procedures that are needed to have a reliable computing. Here we have the last two criteria that are referred to quantum communication within the computing entity and between computing entities. So the first, the ability to interconvert stationary and flying qubits, is that inside the computing entity you have stationary qubits that are the ones that are processed, quantum mechanically processed to perform the computing operation, but also there are flying qubits moving, are called the flying qubits, the qubits that are moving between or among different entities. So this is fundamental also in the seventh of the criteria, that the transmission of qubits, of flying qubits, should be possible not only within the individual computing entity, but also if you have distributed computing entities, so a network of computing entities. So the quality of these interfaces inside the device or between devices should allow reliable flying qubits. So now we mentioned in one of the criteria the terminology universal gate sets. So the gates are basic instructions that are not decomposed into further sub-instructions. So are the basic bricks, the atoms that are used to build all the computing building. So a set of gates that allow to compute any function is called a universal gate set. And the task of implementing a specific function is called a computational problem. So you have a function, you use gates, so basic instructions, to compute that function, so to solve that computational problem, and a set of gates that allow to compute any function, so general function, is a universal gate set. So in classical computing, we know you had for sure courses about Boolean gates when you had like Boolean logic courses or electronic circuits, etc. So not, and, whatever. These are the Boolean gates, and they can be used in our computers, phones, whatever. They are used to compute any function. So they are known also as functional completeness. Then we can say, because of that, that the set of the Boolean gates constitutes a universal gate set. All the Boolean gates together are redundant for universality, so different universal gate sets can be built. So there is not only one universal gate set. Because of the redundancy of the Boolean gates, the number of Boolean gates, there are possible universal gate sets that can be constructed. So, for example, one universal gate set is given by AND and NOT. So, this expression, so the expression saying a gate is or is not universal, is used to say that as a single element, the gate represent a universal gate set, and not if it's an element of a universal gate. So if you read the expression a gate is universal, means that that gate represents a universal gate set. So if we think now about quantum computing, quantum computation, we have to find that all the possible quantum operation can be approximated by a small set of fixed quantum operations, as we had for the classical computing. So we have to find a universal quantum gate set. And this set will represent the basic model for the quantum computation. So by now, different models exist. So I say, I want to say that today, nowadays, even if various companies and various academic entities can say that they have like as in the articles, for example, that I showed you in the second lecture, I think, at the beginning of the second lecture, about Google and IBM saying we have the quantum computer processing this number of qubits. So their computers are individual instances. So by now there is not a quantum processing standard architecture. So it's not defined because it's still an open challenge. We are researching that in the scientific community still. So there is not a specific universal quantum gain set, but there are by now circuits, so circuit models that have already been identified that very likely will be elements of the future universal quantum gate set that will be structured. So, as I said, these circuits are graphical representation of quantum algorithms. The building blocks of these circuits that now I will show you, the main building blocks, are representing one of the functions of the quantum operations that we have seen in all the previous lectures. And the measurement, as I said in one of the previous slides, is at the end, because once you measure the qubit, then you cannot, this is not unitary evolution, so then you destroy the coherence of the quantum system. So now let's start with this overview, rapid overview of the gates. Here I list now all the gates that we will see in the first lecture in January next year, in which we will apply and combine these gates in order to see some quantum algorithms interactively. So now I just give you a brief list and characteristics of these building blocks. For example, the Hadamard gate is very important, is used to create the qubit, the linear combination, the superposition of the bases. So the specific superposition. This is the APR pair that we have already seen in various slides of the previous lectures and this lecture. So then here, for example, you understand why I was introducing the Pauli matrices when talking in one of the previous lectures, talking about the spin and the representation of a spin connected to the Lie algebra and the Lie parentheses. So regarding the momentum. If here we use this X gate as a single qubit, because you see that there is only one line. This Pauli matrix that is called X You remember there are 3 Pauli matrices that we have seen, and this is one of them. And this Pauli matrix is used to perform what in the classical computing is not. So we see that it flips the basis. Here we see that this second Pauli matrix changes the bit and the phase. Sorry, the basis and the phases. The third Pauli matrix instead changes just the phases in the qubit. Here we have the general phase gate. Sorry, not the general. We have the phase gate referred, because there is I, referred to a rotation of a change of the phase of pi, the half of pi. And here we have the general phase gate that implies a shift rotation of the phases of the qubit. Then we have here the measurement gate. You see that the single line represents the quantum world, and the output are 2 lines, the 2 bits that you get by measuring the qubit. So the thing is, the output here of 2 lines is classical. So here you have classical bits, and here you have the qubit. So after this gate, the unitary evolution stops. So here is the coherence of the qubit of the quantum system is destroyed. You get the output considering the probabilistic description that we saw in the previous lectures, and then you proceed with the computing, or you get the classical values. But you cannot come back. Then we can say that if we have a sequence of a series of classical gates, the total operation is represented by the product of the matrices that the gates were performing individually. Then we have 2 qubit gates, and these gates use a qubit and perform operation on the qubits according to a control, so according the value of another qubit. So here we have the general controlled U-gate. This general controlled U-gate can perform a controlled operation of the Pauli matrices, the Pauli gates that we have seen before, that were for single qubits. Here we have their controlled versions. If you, for example, replace U with the Pauli matrices, and in fact, we have, for example, the control Z gate that has the Z Pauli matrix here. So there is another gate that swaps. We have this gate that swaps the 2 qubits. You can see here. And then we have also the gates for, then we have also the gates for entanglement. So these gates consider the creation of an entangled pair. So it can be a Bell state, so the entanglement, the states that we show the PR pairs, or more than one qubit, so the entanglement between several qubits, and this is called GHZ states, and these are the algebraic structures of these states. Then we have the Toffoli gate, that is a 3-qubit gate. So there is a controlled CNOT in this case. And so finally, we say that some operations we saw are not possible in quantum, according to what we have said. Some operations are not possible in quantum domain, because as we saw that acting on a qubit can reduce the coherence, or can destroy the status of the qubit, then we see that loops, for example, are not allowed. Or the fact that this so-called no cloning theorem normally says that it's not possible to copy a quantum system. So what we do, this is another hard implementation problem, limit for quantum computing and communication entities. So the states, the qubits cannot be copied, reproduced. And also, for example, fan-in, fan-out operations are not possible in quantum computing. So there are various operations that are not possible or restricted in quantum computing and communications. Finally, I just mentioned another graphical representation just for curiosity. Penrose diagrammatical representation of quantum of tensor networks are quite useful, and started the field of representation of quantum systems and quantum multiparticle entangled systems, representing via these so-called diagrams. These are some of the basic building blocks. So you see that, for example, the basic elements that we have seen in our lectures on quantum mechanics, you have complex scalar, you have the ket, you have the bra, so the dual vector. So you can define their scalar product, you can define it graphically in this way, so combining the bra and the ket, and this can become their outer product. So this will become a matrix. So, it is possible to, like when the calculations of the characteristics of complex quantum systems become quite difficult, it is possible to use these diagrams to like have a graphical depiction of the quantum properties of complex entangled systems. And these graphs, actually, these tensor networks helped to find some properties of entanglement that were quite hard to see in mathematical form. So here is our conceptual summary again. So today we have seen an example of entanglement, how entanglement can exceed performances of classical communications, distributed computing, achieving with quantum games using entanglement as an additional strategy, exceeding the performances, so maximizing more the payoff function of these cooperative games. Then we discussed the Di Vincenzo criteria, the characteristics of quantum computing and a quantum communication system should have, the critical aspects, and we saw the graphical translation of all the concepts, let's say most of the concepts that we have seen in the preliminaries, into the quantum gates, so that we will see in the next lecture next year the combination of these gates for quantum algorithms. So I thank you very much for your attendance, and I wish you a nice Christmas time and New Year's Eve.